Alpha Centauri is the closest star system to our Sun. Every astronomy textbook will tell you it lies just 4.24 light-years away. And at first, that number feels small, almost approachable, something that sounds within reach. It even feels like a sensible first destination for an interstellar civilization. But it is none of those things. When that distance is translated into kilometers, it becomes roughly 40 trillion. And when we estimate how long our fastest spacecraft would take to cross that gap, the answer stretches beyond 70,000 years. Even if you imagine traveling at 20% of the speed of light, the journey would still last more than 2 decades, with another 4 years needed just for a signal to return. And suddenly the number loses any sense of simplicity. The nearest star is not close at all. It stands more like a boundary, something vast and unyielding. And to understand that boundary, we need to look at what it truly represents. If you find this kind of perspective calming to explore, you can stay with me for the rest of the journey, as we slowly unfold just how vast this distance really is. There is a star system that nearly every astronomy student encounters within their first week of study. It appears across introductory textbooks, on star charts, and in countless documentaries exploring the search for life beyond Earth. It carries a name that even those with a casual interest in space have likely heard before. Alpha Centauri, the closest star system to our own. It lies within the southern constellation of Centaurus, visible as one of the brightest points in the night sky for observers located south of roughly 40 degrees north latitude. To the naked eye, it appears as a single, steady point of light, but through a small telescope, it separates into 2 distinct stars, orbiting one another in a slow gravitational dance that takes about 80 years to complete. These are known as Alpha Centauri A and Alpha Centauri B. A third companion exists much farther out, far dimmer than the other two, a small red dwarf called Proxima Centauri. Together, the 3 form a triple star system, one that carries a title that almost feels welcoming, the closest stars to our Sun. Alpha Centauri A is strikingly similar to our Sun. It is a G-type main sequence star, slightly more massive, a little larger, and a bit more luminous. If you were standing on a planet within its habitable zone, the light above you would feel strange. Alpha Centauri B, by contrast, is a K-type star, somewhat smaller and cooler than the Sun, yet still a stable and bright stellar source in its own right. These 2 stars orbit each other at distances that shift between something like the orbit of Saturn and that of Neptune in our solar system, moving closer and farther apart over their roughly 80-year cycle. Together, they form a binary system that has remained gravitationally bound for billions of years, likely forming around the same time as our Sun, somewhere between 4.5 and 5 billion years ago. And then there is Proxima. Proxima Centauri is a small, dim star known as a red dwarf, containing only about 12% of the Sun's mass and emitting only a small fraction of its light. It is so faint that even though it is the closest individual star to Earth, it cannot be seen with the naked eye, requiring a telescope to detect it at all. Proxima orbits the Alpha Centauri A and B pair at an immense distance, around 13,000 astronomical units away, taking roughly 500,000 years to complete a single orbit. For many years, astronomers were unsure whether it was truly bound to the system. It was only in 2017 that precise radial velocity measurements confirmed the connection. Proxima is indeed part of the system, just an extremely distant and faint member, and at present, it holds the title of the closest star to our Sun. Its distance from Earth is about 4.24 light-years, while Alpha Centauri A and B are slightly farther at around 4.34 light-years. The difference is small, only about 1/10 of a light-year, simply because Proxima is currently positioned on the side of its wide orbit that faces us. And this alignment is only temporary on cosmic timescales. Over tens of thousands of years, Proxima will continue drifting along its orbit around the central pair, and in time, Alpha Centauri A or B will take turns becoming the closest star to our Sun. But for now, in the present moment, Proxima holds that distinction, 4.24 light-years, The nearest star. Say that number slowly. 4.24 light-years. It has a clean and compact feel, something that fits easily into a sentence, simple to remember and easy to repeat. Compared to most distances in astronomy, it seems small. The Milky Way stretches across roughly 100,000 light-years, and the Andromeda Galaxy lies about 2.5 million light-years away. The observable universe extends to around 93 billion light-years, and against those scales, 4.24 begins to feel almost like a neighbor. It gives the impression of a distance an advanced civilization might realistically attempt to cross, something like a first step, a starting point, an achievable goal. But this is the illusion, and it is one of the most misleading intuitions in all of space science. Because 4.24 light-years is not small, not manageable, and not a practical first step. It is a distance so vast that the human mind is not equipped to fully grasp it. And even the language of astronomy tends to soften its scale, making it feel more approachable than it truly is. So instead of leaving it as an abstract number, we can begin to express it in more familiar terms. 1 light-year is the distance light travels in a single year, moving at about 186,000 miles per second. Over that time, light covers roughly 5.9 trillion miles. Multiply that by 4.24. And the distance to Proxima Centauri becomes about 25 trillion miles. That distance can also be expressed in another way, about 268,000 astronomical units, where 1 AU represents the distance from Earth to the Sun. Even then, the numbers remain far beyond anything we can easily visualize. They still feel abstract, too large to carry meaning on their own. So instead of leaving them as raw figures, we can begin to build some context, step by step. Starting with the one speed every human instinctively recognizes as fast, light is the fastest thing in the universe. Nothing that carries mass or information can travel faster. A beam of light moves from Earth to the Moon in about 1.3 seconds. It reaches the Sun in roughly 8 minutes and 20 seconds. It passes the orbit of Neptune, the outermost major planet, in around 4 hours. Light is so fast that it can circle the Earth 7.5 times in a single second. There is no greater speed, no more absolute limit, and even so, light itself still takes more than 4 years, and roughly 3 additional months, to reach Proxima Centauri. Consider what that really means. A photon leaving Earth right now, traveling at the maximum speed allowed by physics, would not arrive at the nearest star until sometime around the year 2030. If you were to shine a flashlight toward Proxima Centauri tonight, the very first photon from that beam would arrive only after the next United States presidential term has ended, after the next Olympic Games have taken place, after thousands of cycles of news and change have passed, and that is still the fastest journey possible. Nothing with mass can match it, and nothing humanity has ever built has come close. So now we can begin to consider the emptiness that fills those 4.24 light-years. The space between stars is not simply distant, it is empty in a way that nothing on Earth can truly prepare you for. The average density of interstellar space in our region of the galaxy is about 1 atom per cubic centimeter, a vacuum so extreme that even the best laboratory vacuums on Earth are millions of times denser. Between here and Proxima Centauri, there is almost nothing, no significant gas cloud, no wandering planets that we have confirmed, no asteroids, no comets, no markers, no landmarks. Just a vast stretch of near-perfect emptiness extending for about 25 trillion miles. To begin sensing this scale, imagine compressing the entire solar system so that the Sun becomes a basketball placed at the center of a football field. At this scale, Earth would be a tiny grain of sand sitting about 26 meters away. Jupiter would appear as a small marble at roughly 130 meters. Neptune, the most distant major planet, would be a small pebble about 3/4 of a kilometer from the basketball, and Voyager 1, the most distant human-made object, would be a nearly invisible speck, roughly 4.5 kilometers away after almost 50 years of continuous travel. At this same scale, Proxima Centauri would appear as another basketball placed about 4,300 miles away, roughly the distance from New York City to Rome. The entire solar system, everything humanity has ever visited or even sent a probe toward, occupies a region that fits within just a few miles around that basketball. The nearest star, by contrast, sits on another continent entirely. Between those two basketballs, across those 4,300 miles of scaled distance, there is nothing, no structure, no resting point, no intermediate destination, only the equivalent of crossing the Atlantic Ocean and much of Western Europe with nothing beneath you but empty vacuum. This is the reality hidden behind the phrase 4.24 light-years. It sounds like a number you could work with, but it is something else entirely. It is, in a very real sense, un arbus. And there is another way to understand that gap. Consider the signals we use to communicate with our most distant spacecraft. Voyager 1, launched in 1977, is currently the farthest human-made object from Earth. As of early 2026, it is about 172 astronomical units from the Sun, which corresponds to roughly 16 billion miles. A radio signal sent from Earth reaches Voyager 1 in just under 24 hours. In fact, by November of 2026, Voyager 1 is expected to cross the milestone of being one full light day away from Earth for the first time, and that moment is worth pausing on. The most distant object humanity has ever created. After nearly 5 decades of continuous travel at roughly 11 miles per second, is only just reaching the point. Proxima Centauri, by comparison, is about 1,550 light days away. After almost 50 years of travel, Voyager 1 has covered only about 0.06% of the distance to the nearest star. If you were to draw a line across a football field to represent the full journey to Proxima Centauri, Voyager's progress since 1977 would be a mark just a couple of inches from one end, about the width of 2 fingers along a 100-yard line. This is not a metaphor. It is simple arithmetic. The emptiness between here and Alpha Centauri is not a gap in the way an ocean is a gap, or a desert is a gap. An ocean has current, islands, and weather systems that break the journey into segments. A desert has horizons, occasional oases, and the quiet assurance that something lies on the other side within a human lifetime. The interstellar void offers none of that. It is a gap without features, without milestones, without any intermediate scale. It is pure distance, uninterrupted by anything that might make it feel traversable. And this is what makes the distance especially deceptive. Alpha Centauri is bright. It is the 3rd brightest star system in the night sky, outshone only by Sirius and Canopus. For observers in the southern hemisphere, it shines prominently with an apparent magnitude of about -0.27. making it an unmistakable feature of the sky. You can step outside on a clear night in places like Sydney, Santiago, or Johannesburg and see Alpha Centauri without any optical aid. It appears close, almost like a neighbor, and the sheer brightness of its light creates the instinctive feeling that its source cannot be very far away. But what you are seeing when you look at Alpha Centauri is light that left the system more than 4 years ago. The photons reaching your eyes today departed from Alpha Centauri A and B when the calendar on Earth still read 2021 or 2022. You are not seeing the stars as they are now. You are seeing where they were and how they shone years in the past. And that delay itself becomes a measure of the distance. Every year of light travel represents about 5.9 trillion miles of empty space that those photons had to cross before arriving at your retina. And even the brightness can be misleading. Alpha Centauri A is naturally quite luminous, about 1.5 times the brightness of our Sun. But the main reason it appears so bright in our sky is simply because it is relatively close. If you were to move Alpha Centauri out to a distance of 10 parsecs, the standard reference used for measuring stellar brightness, it would fade to an unremarkable apparent magnitude of around 4.38 for the A component alone. At that point, it would become just another faint and forgettable star in a crowded sky. Its brilliance, then, is largely an effect of proximity. And that proximity, in absolute physical terms, still amounts to roughly 25 trillion miles. Humans evolved to judge distance using visual cues. Bright objects tend to feel closer, while dim ones seem farther away. This instinct works well in environments like the African savanna, where the brightness of a fire can reliably indicate how far away a campsite might be. But in astronomy, that same instinct fails completely. Sirius, the brightest star in the night sky, is actually almost twice as far away as Alpha Centauri. Canopus, the second brightest, lies more than 70 times farther. In the stellar world, brightness is determined by intrinsic luminosity, not simple proximity, and the visual instincts we evolved are not just unhelpful, they can be deeply misleading. When you look at Alpha Centauri and feel that it is close, your mind is applying a rule that no longer works once you leave Earth's atmosphere. We can also approach this problem of scale through time. Humans have known about Alpha Centauri as a star for thousands of years. Ancient navigators in the southern hemisphere used it as a reference point, but its actual distance has only been understood for less than 2 centuries. In 1832, Thomas Henderson, working at the Royal Observatory at the Cape of Good Hope, began a series of careful positional observations that would eventually lead to the first measurement of Alpha Centauri's parallax. The tiny apparent shift in its position caused by Earth's motion around the Sun, Henderson calculated a value that suggested Alpha Centauri was astonishingly distant. So distant that he initially hesitated to publish his results, suspecting they might be incorrect. He eventually released them in 1839. Shortly after Friedrich Bessel announced a similar measurement for 61 Cygni the year before, Henderson was right. Alpha Centauri was not a nearby point of light. It was a distant sun, separated from our own by a vast emptiness that no technology of that era could even begin to imagine crossing. Nearly 2 centuries later, we have measured that distance with remarkable precision. Using spacecraft such as the European Space Agency's Gaia Observatory, which has refined stellar parallax measurements to accuracies of just millionths of an arcsecond. The current best estimate places Proxima Centauri at a parallax of 771.64 milliarcseconds, corresponding to a distance of about 4.2465 light-years. We now know exactly how far away it is. The number is not uncertain, and it is not an estimate. The distance has been measured with a level of precision that Henderson could never have imagined. And yet that precision changes nothing about the underlying problem. Knowing the distance to within a fraction of a light-year does not make it any shorter. It does not make the void any less empty. It does not bring the nearest star even a single mile closer to our reach. Precision in measurement and the ability to physically reach a destination are entirely separate things. And Alpha Centauri reveals that distinction with striking clarity. There is one more layer to this illusion that needs to be considered before we continue. And it lies in the word nearest itself. In everyday language, the word nearest suggests accessibility. The nearest store is somewhere you can drive. The nearest hospital is somewhere you can reach in an emergency. The nearest friend is someone you can visit on a quiet weekend. The word carries an assumption that closeness implies reachability. In astronomy, that assumption breaks down. The nearest star is not the one we can reach. The nearest star is simply the least unreachable one. And that difference is more important than it first appears. It is also a distinction that is rarely made explicit. Proxima Centauri is the closest star to our Sun. It is also, by any engineering standard available to human civilization today, completely beyond our reach. Not difficult to reach, not expensive to reach, not impractical to reach, but unreachable. The technology required to send a functioning spacecraft to Proxima Centauri and have it arrive within a human lifetime does not exist. It is not being built, and it is not even in a testing phase. The propulsion systems that would be needed to make that journey in less than several thousand years have never been constructed at any meaningful scale by any nation for any purpose. The nearest star is a destination we can observe, measure, and study in remarkable detail from a distance of roughly 25 trillion miles. But we cannot go there, and that is the core of the illusion. Alpha Centauri occupies a strange and uneasy place in our understanding of space. It is close enough to be seen with the naked eye, close enough to be measured with extraordinary precision, close enough that we have already detected planets orbiting one of its stars. And yet it is distant enough that no propulsion system ever tested by humanity could deliver a spacecraft there within the span of recorded history. It is, at the same time, the most accessible and the most inaccessible destination in the galaxy, the nearest star, and yet nowhere near. Alpha Centauri is not just a point of light in the southern sky. It is a kind of test case. The simplest version of a problem that becomes even more unforgiving for every other star beyond it. If we cannot truly grasp the distance to the nearest star, then we cannot understand interstellar space at all. And if we cannot imagine a realistic mission to Alpha Centauri, then every other destination among the stars becomes even more unreachable. The distance to Alpha Centauri represents the baseline of interstellar travel, the absolute minimum challenge. Everything beyond it is more difficult. And even this starting point is already impossibly high. We know the numbers, we know the distance in miles, in astronomical units, in light years. We understand how long light takes to cross that gap. And we know how little of it our fastest spacecraft has managed to cover in half a century of flight. We know the void is empty, featureless, and uninterrupted by any landmark or waypoint. We know the star is bright, visible, and close in astronomical terms, yet impossibly distant in engineering terms. But numbers alone cannot fully convey what this distance means for an actual journey. To understand why Alpha Centauri is not just far, but profoundly distant, we need to stop measuring and begin thinking in terms of motion. We need to ask what happens when a real spacecraft is pointed toward the nearest star and pushed as hard as current technology allows. That is where the true difficulty begins. So let us do something that most discussions tend to avoid. Instead of treating this distance as an abstract number, we can begin to approach it as an engineering problem, not a thought experiment, but a real problem involving real spacecraft, real velocities, real power sources, and real material limits. The moment we do that, the distance shifts from something theoretical into something that feels physically hostile. And the best place to begin is with the fastest object humanity has ever sent beyond the solar system, Voyager 1. Launched on September 5, 1977, Voyager 1 completed its original mission studying Jupiter, then continued outward, using gravitational assists from both planets to increase its speed to about 11 miles per second relative to the Sun. That is roughly 38,000 miles per hour. As of early 2026, Voyager 1 is about 172 astronomical units from the Sun, making it the most distant human-made object ever created. A speed of 11 miles per second is extraordinarily fast by any human standard. It is more than 15 times faster than a rifle bullet, and roughly 50 times the speed of sound at sea level. If you could maintain that velocity along Earth's surface, you would circle the entire planet in about 39 minutes. Voyager 1 covers a distance equal to Earth's diameter in roughly 12.5 minutes. It travels from Earth to the Moon in about 6 hours. By any measure of human engineering, it is incredibly fast. And yet, if you point it toward Proxima Centauri, the picture changes completely. The distance is about 4.24 light years, or roughly 268,000 astronomical units, which corresponds to about 25 trillion miles. At 11 miles per second, Voyager 1 would need approximately 74,000 years to cover that distance. 74,000 years. That is not a travel time. It is a geological timescale. 74,000 years ago, modern humans had not yet spread widely beyond Africa. and the most recent ice age had not yet reached its peak. Agriculture did not exist. Writing did not exist. Cities and empires had not yet formed. All of recorded human civilization fits within a span of only 5,000 to 6,000 years. Voyager 1 would require more than 12 times that entire span just to reach the nearest star. And yet, Voyager 1 is not even heading toward Alpha Centauri. Its path carries it in a completely different direction, toward the constellation Ophiuchus. And the closest star it will approach is a faint red dwarf known as Gliese 445. It will pass that star in about 40,000 years. At a distance of roughly 1.7 light-years, Voyager 1 was never intended to reach another star. It was built to study Jupiter and Saturn. The fact that it is still operating and transmitting data after nearly 50 years is a remarkable achievement of engineering. But its speed and trajectory were never designed for interstellar travel. It remains simply the fastest object humanity has ever sent outward. And it serves as a useful reference point for understanding why our current technology is so limited when it comes to crossing interstellar distances. So we can ask a natural question: what happens if we try a different spacecraft? New Horizons, the probe that passed Pluto in July of 2015, is currently traveling at about 9 miles per second relative to the Sun, which is actually slower than Voyager 1. At that speed, the journey to Proxima Centauri would take around 87,000 years. That is not an improvement. It is worse. New Horizons is a more modern spacecraft than Voyager, built with decades of additional engineering experience. Yet it moves more slowly on its outward path because it benefited from less favorable gravitational assists. So, what about the Parker Solar Probe? Often described as the fastest spacecraft ever built. Here, the numbers need to be understood carefully. Parker Solar Probe reaches its record speeds not while escaping the solar system, but during close passes near the Sun, where it falls deep into the Sun's gravitational well and accelerates to extreme velocities at its closest approach. At that point, it has reached speeds exceeding 118 miles per second relative to the Sun, more than 11 times faster than Voyager 1. It sounds like a breakthrough, but it is not. That extreme speed exists only at the lowest point of its orbit, deep within the Sun's gravity. As the probe climbs outward again, it slows significantly, trading speed for altitude. Much like a ball thrown upward loses momentum as it rises. Parker Solar Probe cannot maintain 118 miles per second on a straight outward path. That speed is effectively borrowed from the Sun's gravity, and it must be given back. Even if it was somehow redirected at that moment into a direct escape trajectory, the speed it could sustain would be far lower, limited by the same gravitational constraints that affect all spacecraft leaving the solar system, even if we imagine, unrealistically, that it could maintain its peak speed for the entire journey. The trip to Proxima Centauri would still take about 6,700 years. That is longer than all of recorded human history. Longer than the time from the invention of writing to the present day, and it assumes a speed no spacecraft has ever sustained, and no current technology can maintain beyond a brief solar pass. The numbers remain unforgiving. At around 62 miles per second, a speed no outbound spacecraft has achieved, the journey would still take roughly 12,700 years. At about 310 miles per second, a velocity that does not exist in current engineering, the trip would still take around 2,500 years. Even at 620 miles per second, an extreme speed beyond any propulsion system under development, the crossing would still require about 1,260 years. No matter how the numbers are adjusted, no matter how optimistic the assumptions become, the result always returns in centuries or millennia. The distance does not bend to our expectations. Let us consider what these timescales actually mean for mission design. Because the issue is not simply that the journey takes a long time. The deeper problem is that no spacecraft and no mission architecture we can build is capable of surviving for that long. We can begin with materials. Every spacecraft ever constructed has a limited structural lifespan. Components degrade over time. Metals slowly fatigue. Seals lose their integrity, and lubricants evaporate into the vacuum. Radiation gradually damages electronics, flipping bits in memory, degrading solar cells, and weakening structural bonds. Even the most durable spacecraft we have ever built, the Voyager probes, are already showing clear signs of aging after less than 50 years. Their radioisotope power systems are steadily losing output. Instruments have been shut down one by one to conserve what little energy remains. Their onboard systems rely on technology designed in the 1970s. Voyager 1 is still operating, but only just. It continues to function at the very edge of its intended lifespan, sustained by careful intervention from engineers on Earth, sending commands that take nearly a full day to arrive. Now imagine asking that spacecraft, or any spacecraft, to survive not for decades, but for 74,000 years. The challenge is no longer difficult, it becomes absurd. No material we have ever produced can maintain its structural integrity for that length of time without maintenance. No electronic system can operate for thousands of years without failure. No power source available today can provide energy for more than a few centuries at most. Even radioisotope generators, the standard for deep space missions, have half-lives measured in decades, not in millennia. Solar panels become ineffective far beyond the outer solar system, where sunlight fades to almost nothing. Nuclear fission systems depend on fuel that decays and control mechanisms that degrade. Every power system we currently possess runs out on timescales that are far shorter than the journey to Alpha Centauri at present speeds. And then there is the question of communication. Voyager 1 transmits data back to Earth at a rate of roughly 160 bits per second. Using a 23-watt transmitter and a high-gain antenna about 12 feet across. Even at its current distance, the signal that reaches Earth is so faint that it requires the massive 70-meter dishes of NASA's Deep Space Network to detect it. Signal strength decreases with the square of distance. If you double the distance, the signal becomes 4 times weaker. At the distance of Alpha Centauri, about 268,000 astronomical units, the signal from an identical transmitter would be millions of times weaker than what we receive today. No radio telescope that exists today could detect a signal that faint. Not the Deep Space Network, not the Green Bank telescope, not even a theoretical array far larger than anything we have ever constructed. The inverse square law does not bend. It simply reduces the signal without mercy. To maintain communication across interstellar distances, you would need transmitters far more powerful than anything we currently use, or antennas vastly larger, or both. But every addition increases mass, and mass works directly against speed. Every pound added to a spacecraft must also be accelerated to interstellar velocity. That demands more fuel, which adds more mass, which in turn requires even more fuel. The rocket equation turns even small increases in communication hardware into a cascade of added propellant. The total mission mass grows rapidly, caught in a feedback loop that is difficult to escape. And even if communication could somehow be maintained, a deeper issue remains. At the speed of Voyager 1, the journey would last around 74,000 years. Who would still be listening after that span of time? What institution could maintain a receiver for tens of thousands of years? What civilization would even remember that the mission was ever launched? The oldest continuously operating human institutions, such as certain religious orders and universities, reach back only about 1,000 years. The oldest known human structures are roughly 12,000 years old. No government, no culture, no belief system has endured for 74,000 years. Not even remotely close. Sending a spacecraft on a journey that long is not really a mission plan. It is a belief, an assumption that civilization will persist unchanged across spans of time for which we have no precedent at all. A common response appears almost immediately. If a single human cannot survive the journey, then perhaps many could. Why not build a vessel large enough to support an entire population across generations? A self-contained world moving through the void, where people are born, live their lives, and pass away while the ship slowly continues toward its destination. This idea is known as a generation ship, and it has been a recurring concept in science fiction for nearly a century. At first, it seems elegant, but under closer examination, it begins to fall apart. We can begin with biology. A population confined within a closed system for 74,000 years would need to preserve enough genetic diversity to avoid the long-term effects of inbreeding. This leads to the gradual accumulation of harmful recessive traits, which occurs when a relatively small population continues to reproduce within itself over many generations. Research in population genetics, including studies focused on long-duration space missions, suggests that a viable population for a multi-generational journey would likely need to be in the thousands, not the hundreds. Some estimates place that threshold at around 4,000 to 5,000 individuals in order to preserve sufficient genetic diversity over centuries without heavy genetic intervention. Other models suggest the number could be reduced with careful reproductive planning, but even the most optimistic scenarios still require at least several hundred individuals at the very beginning, along with strict controls on reproduction maintained across every generation for the entire journey. And several hundred people is not a crew. It is closer to a small town. A community of that size requires food production, water recycling, waste management, medical systems, education, governance, conflict resolution, and all the other structures that sustain human life over time. Every one of those systems would need to function without outside support for 74,000 years. There would be no resupply, no spare parts arriving from Earth, no emergency deliveries of seed, medicine, or rare materials. The ship would need to carry, or somehow produce, everything its population might ever require, across a span of time roughly 15 times longer than all of recorded human history. No closed ecological system has ever come close to that level of self-sufficiency. Biosphere 2, one of the most ambitious attempts to create a sealed environment on Earth, experienced severe oxygen loss and crop failures within just 2 years. Despite operating under stable gravity, abundant sunlight, and immediate access to external intervention, the International Space Station, the most advanced space habitat ever built, depends on constant resupply from Earth, with tons of food, water, equipment, and replacement parts delivered multiple times each year. A generation ship would need to reproduce the stability of an entire planetary ecosystem, relying only on the resources loaded at launch, with no margin for large-scale failure across thousands of years. The engineering challenge alone is immense, but the social challenge may be even greater. A generation ship is not simply a machine, it is a civilization in motion, and civilizations do not remain unchanged over long periods of time. Languages evolve, cultures shift, belief systems rise and fall, and political structures transform, sometimes in unpredictable ways. Over centuries, the values, priorities, and even the basic worldview of a population can change completely. The people who begin the journey would likely share almost nothing culturally with those who arrive tens of thousands of years later. The people who arrive would not speak the same language as those who first departed. They would not share the same beliefs, the same social systems, or even the same understanding of why the mission began at all. And this introduces a deeper ethical question that discussions of generation ships rarely confront directly. The first generation makes a choice to board the vessel. Every generation that follows does not. They are born into an environment they cannot leave, bound to a mission they never agreed to, moving toward a destination they will never see within their own lifetime, nor within the lifetimes of their children or grandchildren. Across hundreds of generations, every individual would live and die in transit, never witnessing either the world of origin or the place they are meant to reach. In a very real sense, they become bound to a decision made by ancestors so distant that they have faded into legend, and that raises difficult questions. What happens when, generations later, people begin to question the purpose of the journey? What happens if a political group takes control of the ship and redirects its priorities? What happens if a belief system emerges that reshapes the mission entirely, or even denies that any destination exists? Over a span of 74,000 years, every form of social disruption is not just possible, but statistically unavoidable. Conflict, resource shortages triggered by ecological imbalance, loss of technological knowledge, or disease spreading through a closed population with no external support. The ship would not need to endure a single crisis. It would need to endure all of them, one after another, for longer than any civilization has ever existed on Earth. In that sense, a generation ship does not solve the problem of distance. It reframes it. Instead of asking whether a machine can survive for 74,000 years, it asks whether a human society can survive that long within a machine. Based on what we understand about human behavior, ecological systems, and population genetics, the answer is almost certainly no. Not because it violates the laws of physics, but because the timescale exceeds every known limit of human endurance, both socially and biologically, by an enormous margin. The distance to Alpha Centauri does not only challenge our machines, it challenges our species itself. At current speeds, the journey is too long for electronics, too long for materials, too long for institutions, and too long for human populations confined within artificial environments. The problem is not one of determination or engineering alone. It is a problem of time, and at 11 miles per second, there is simply too much of it. There is also the problem of navigation across such a span. Over tens of thousands of years, even the smallest error in direction or velocity can grow into something enormous. A deviation of just 1,000th of a degree at launch would result in a missed distance of roughly 435 million miles by the time of arrival. Several times the distance between Earth and the Sun. Mid-course corrections require thrusters that still function, navigation systems that remain accurate, and onboard computers that continue to operate reliably. All of these systems would need to work not just for decades, but for tens of thousands of years. No propulsion system can store fuel for that long, and no sensor can maintain precise calibration across such timescales. No computer we have ever built can operate without failure for even a few centuries, let alone thousands of years. And, beyond the spacecraft itself, the environment between the stars introduces its own hazards. While interstellar space is incredibly empty by Earth standards, it is not a perfect vacuum. Tiny dust particles, some only a few microns across, drift through this space at relative speeds that depend on the motion of the spacecraft, at around 11 miles per second. Even a collision with a microscopic grain carries energy that scales with the square of that velocity. Over a journey lasting 74,000 years, the chance of encountering particles large enough to damage critical systems is not insignificant. There is no shielding technology capable of protecting a spacecraft from every possible impact over such a long duration. The interstellar medium may be sparser, but time is vast, and probability accumulates. So we can step away from Voyager-level speeds and look toward propulsion systems that are either under development or within near-term engineering reach. One of the most promising approaches for deep space travel is ion propulsion. Instead of burning fuel in short, intense bursts, ion engines use electric fields to accelerate charged particles, producing a gentle but continuous thrust that slowly builds velocity over time. NASA's Dawn spacecraft, which orbited both the asteroid Vesta and the dwarf planet Ceres, demonstrated how effective this method can be, achieving significant changes in velocity over the course of its mission. However, even with this advantage, ion engines still fall short. Their exhaust speeds, while much higher than chemical rockets, typically reach only about 20 to 30 miles per second, even after years of continuous acceleration. The final speed of the spacecraft remains far below what would be required for interstellar travel. More advanced concepts, such as the Variable Specific Impulse magnetoplasma rocket, often referred to as VASIM, promise greater efficiency and higher exhaust speeds. In theory, Systems like this could push spacecraft faster than traditional ion engines, but even under optimistic assumptions, projected velocities remain well below 60 miles per second. At those speeds, a journey to Proxima Centauri would still take more than 12,000 years. Ion propulsion is extremely effective within the solar system, but it is not enough to bridge the gap between stars. Another approach is nuclear thermal propulsion. In this design, a nuclear reactor heats a propellant, usually hydrogen, to extremely high temperatures before expelling it to generate thrust. This produces more force than ion engines and higher exhaust speeds than conventional chemical rockets. Programs such as NERVA in the 1960s demonstrated that this concept worked. Modern versions are being explored for future crewed missions to Mars. But even so, the achievable exhaust speeds reach only about 5.5 miles per second. That is actually slower than Voyager 1's current speed relative to the Sun. Nuclear thermal propulsion can shorten travel times within the solar system, but it does not come close to solving the problem of interstellar travel. Another concept, nuclear pulse propulsion, proposed in Project Orion during the late 1950s. Imagine detonating nuclear devices behind a spacecraft and using the resulting shockwaves for propulsion. Theoretical models suggested that such a vehicle could reach speeds of around 3 to 5% of the speed of light, reducing the journey to Proxima Centauri to roughly 85 to 140 years. A dramatic improvement over 74,000 years. But Project Orion was never built. It was ultimately abandoned for several reasons, ranging from the Partial Nuclear Testban Treaty of 1963, which prohibited nuclear detonations in space, to the immense engineering challenge of constructing a pusher plate capable of surviving repeated nuclear blasts. The idea remains intellectually compelling, but in practical terms, it does not exist. No hardware has ever been built. No real-world tests have been carried out. And no government or institution is actively developing an Orion-class system. A step beyond fission-based designs is nuclear fusion propulsion, explored in concepts such as Project Daedalus, a 1970s study by the British Interplanetary Society for an uncrewed interstellar probe. The design proposed igniting pellets of deuterium and helium-3 inside a reaction chamber, producing exhaust speeds of about 6,200 miles per second. Enough to accelerate a payload of roughly 450,000 kilograms to around 12% of the speed of light. At that velocity, the journey to Proxima Centauri would take about 36 years. For the first time, the trip falls within a human lifetime. But Daedalus never moved beyond theory. The engineering challenges are immense. Sustained fusion ignition at the required rate, hundreds of reactions per second, has never been achieved in any laboratory. The fuel itself, helium-3, is extremely scarce on Earth, with the most accessible supply found in lunar soil at concentrations of only a few parts per billion, which means extracting enough fuel for a single mission would require mining and processing vast quantities of material from the Moon. The spacecraft itself would be enormous, with a fully fueled mass exceeding 50,000 metric tons, larger than an aircraft carrier. Daedalus was never intended as a construction plan, but as a proof that interstellar travel is not forbidden by physics. It demonstrated possibility, but it did not provide a solution. Across all of these propulsion methods, a clear pattern emerges. Chemical rockets are far too slow. Ion engines are efficient but insufficient. Nuclear thermal systems offer only marginal improvements. Nuclear pulse propulsion might work in theory, but it remains both restricted and unbuilt. Fusion propulsion could, in principle, reach meaningful interstellar speeds, but it depends on technological advances and resource commitments far beyond anything currently undertaken by human civilization. Every propulsion system that has actually been built and flown results in travel times to Alpha Centauri measured in tens of thousands of years or more. And every system that could, in theory, reduce that journey to decades or centuries exists only on paper. This is not simply a matter of funding or policy. It is a problem rooted deeply in physics and engineering. The energy required to accelerate even a relatively small spacecraft to interstellar speeds is so vast that it exceeds the total energy capacity of most nations. To understand this more clearly, we can look directly at the numbers. Kinetic energy increases with the square of velocity. To accelerate just 1 kilogram of payload to 1% of the speed of light, roughly 1800 miles per second, requires about 4.5 trillion joules of energy. That is comparable to the energy released by roughly 1 kiloton of TNT for a single kilogram. Now, scale that upward. A spacecraft with a mass of 1,000 kilograms would require about 4.5 quadrillion joules, equivalent to the energy of a full-scale thermonuclear weapon. Increase the mass further to 100,000 kilograms, a very modest estimate for a crewed interstellar vehicle, and the required energy rises to roughly 450 quadrillion joules, simply to reach 1% of light speed. And even at that speed, the journey to Alpha Centauri would still take more than 400 years. Increasing the velocity to 10% of the speed of light does not improve the situation easily, because the energy required per kilogram increases by a factor of 100. At that level, a 1,000 kilogram probe would demand around 450 quadrillion joules, comparable to the total yearly electricity production of a mid-sized industrial nation. A crewed spacecraft traveling at 10% of light speed would require energy reserves approaching a significant fraction of the annual energy consumption of the United States for a single mission, and without any guarantee of slowing down at the destination. These are not speculative estimates. They follow directly from the fundamental equation E equals 1/2 mv squared, one of the simplest relationships in classical physics. The cost of interstellar speed is not uncertain. It is fixed by mathematics, and it is enormous. This leads to a more sobering realization. Alpha Centauri is the nearest star system. It represents the shortest possible journey between stars, and even this minimum distance defeats every propulsion system that currently exists. Not because of a lack of intelligence or imagination, but because the scale of the distance and the energy required to cross it place the challenge beyond the present capability of human civilization. When people hear that Alpha Centauri is only 4.24 light-years away, they instinctively compare it to the size of the galaxy and feel reassured. It sounds close, in relative terms, but that way of thinking belongs to astronomy, not to engineering. An astronomer can describe Alpha Centauri as close and be correct within the context of stellar distances. An engineer attempting to design a mission to Alpha Centauri encounters a barrier imposed by physics itself, one that renders the word close essentially meaningless. We have measured the distance with extraordinary precision. We have aimed our fastest machines in its general direction. We have calculated, planned, modeled, and imagined what such a journey might require. And after all of that effort, the conclusion remains both simple and difficult to accept. At the speeds we can actually achieve, the nearest star system is not a destination. It is a limit, a boundary drawn across empty space, separating the regions humanity can reach from those it cannot. But what if that boundary could be pushed further? Not by a small margin, not by doubling or even increasing our speed tenfold, but by orders of magnitude. What if we could travel thousands of times faster, approaching meaningful fractions of the speed of light? This is the promise offered by the most ambitious propulsion concepts ever proposed. They suggest velocities that could reduce the journey from millennia to decades, but in doing so, they introduce an entirely new set of challenges. Problems that are just as daunting as the long timescales they replace. So imagine that the propulsion problem is solved, not gradually, not by extracting small gains from existing technologies, but through a genuine breakthrough. Imagine that a future generation of engineers succeeds in building a spacecraft capable of traveling at 1% of the speed of light, about 1800 miles per second, a velocity roughly 176 times faster than Voyager 1, and far beyond anything ever achieved in human engineering. What would that change? At 1% of light speed, the journey to Proxima Centauri would take around 424 years, a dramatic reduction from 74,000. It is no longer a geological span of time, but a historical one, 400 years ago. In the early 17th century, Galileo had not yet turned his telescope toward Jupiter, and Shakespeare was still alive. The Jamestown colony in Virginia had not yet been founded. A spacecraft traveling at 1% of light speed would not arrive at Alpha Centauri until the late 2400s, by which time the civilization that launched it could be completely transformed, or gone entirely. 424 years is an improvement over 74,000, but it is still far from practical. No human lifespan extends that far, and no government has ever endured that long in a stable form. The oldest nation-states on Earth are only a few centuries old, and even they have changed dramatically over time. A mission that depends on 4 centuries of uninterrupted operation, communication, and institutional continuity is not something that can be planned with any real certainty. It becomes a wager on the survival and coherence of human civilization across a span longer than the histories of the United States, the British Empire, or even modern science itself. But we can continue to increase the speed. At 2% of light speed, about 3,700 miles per second, the travel time falls to roughly 212 years, still beyond any human lifetime, and still longer than the uninterrupted existence of most institutions. At 5% of light speed, around 9,300 miles per second, the journey shortens to about 85 years. Now we begin to approach something that might fit within a single lifetime, at least in theory. A person born at launch could, under ideal conditions, live long enough to witness arrival, assuming that every life support system, every radiation shield, every food and medical system functioned flawlessly for nearly a century. At 10% of light speed, roughly 18,600 miles per second, the crossing takes about 43 years. This begins to resemble a true mission duration, comparable to a professional career or the lifespan of a major institution. Someone involved in designing the mission in their early years might still be alive to receive the data decades later. A probe equipped with autonomous instruments could return findings to a team that still remembers its original purpose. 43 years is long. But it is not beyond the scale of a single human life. It is long in a personal sense, not a civilizational one. At 20% of light speed, around 37,000 miles per second, the journey falls to approximately 21 years. This is the target speed proposed by the Breakthrough Starshot concept when it was introduced in 2016, a crossing to Proxima Centauri in just over 2 decades. Add the 4.24 years required for a return signal traveling at light speed, and the total time from launch to the first data received on Earth becomes about 25 years, a single generation, a career, a lifetime milestone. At last, the timescale enters a range that feels almost conceivable, where a project leader could approve the mission and still reasonably expect to be present when the first results arrive. This is the speed at which interstellar travel begins to appear possible, at least on paper, and it is precisely here that an entirely new layer of challenges emerges. Breakthrough Starshot was perhaps the most ambitious interstellar initiative ever supported by serious funding, announced by Israeli-American entrepreneur Yuri Milner, backed by $100 million in initial research funding, endorsed by the late Stephen Hawking, and guided by an advisory group of leading physicists and engineers. The project set out to demonstrate a proof of concept for light-driven nanocraft, accelerated to 20% of light speed using a ground-based laser system. The core idea was deceptively simple. Construct a phased array of lasers capable of producing a combined output of up to 100 gigawatts. Launch a carrier spacecraft containing thousands of tiny probes, each weighing only a few grams, and attached to a reflective sail about the size of a meter into high Earth orbit. Then direct the laser array at each sail for roughly 10 minutes, using radiation pressure alone to accelerate these miniature spacecraft to a significant fraction of light speed. The probes would then coast toward Alpha Centauri, arriving in about 20 years. Performing a brief flyby, capturing images, and transmitting data back to Earth using their sails as improvised antennas. The concept did not violate any known laws of physics. It relied on existing technologies in early forms. Laser arrays, light sails, miniaturized electronics, and extended them to scales that were ambitious, but not impossible in principle. In the language of its advocates, this was engineering, not science fiction. The physics itself was sound. The real question was whether the engineering could ever be realized within realistic limits of time and cost. As of September 2025, reporting from Scientific American suggested that the Breakthrough Starshot project had effectively entered an indefinite pause. According to physicist Philip Lubin, one of the key researchers, only a small portion of the proposed funding, around $4.5 million out of $100 million, had been spent across roughly 30 research efforts. No full-scale laser array had been constructed. No light sail had been tested at the scale required for interstellar travel, and no nanocraft had been launched on any true interstellar trajectory. The leadership declined interview requests, and a promised progress update had not appeared by the time the report was published. The project was not officially cancelled. It simply stopped advancing, gradually and without announcement. In contrast to the attention that marked its beginning, this outcome is not a reflection of the people involved, many of whom are highly capable scientists contributing valuable theoretical work. It reflects the sheer magnitude of the challenge itself, even in its most optimistic form. Interstellar propulsion using light sails, with no onboard fuel, with payloads measured in grams rather than kilograms, with no ability to slow down at the destination, and no return journey, still requires a laser system capable of generating 100 billion watts of precisely controlled power. For context, the total electrical generating capacity of the United States is on the order of 1.2 trillion watts. The Starshot system would need to produce a significant fraction of that output and concentrate it into a single beam for several minutes during each launch. The infrastructure required to construct, power, and operate such a laser array would rank among the largest engineering efforts in human history. And the array itself is only the starting point. The light sail must endure acceleration forces reaching tens of thousands of times Earth's gravity. It must be reflective enough to capture momentum from the laser without overheating or degrading. It must also maintain its structure and precise orientation during acceleration, with tolerances measured at the scale of microns. The payload carried by each Starshot probe must include imaging systems, a power source, navigation hardware, communication equipment, and even tiny photon thrusters, all compressed into a mass of about 1 gram. The communication link back to Earth must function across 4.24 light-years, using a sail acting as an antenna only a few meters across, transmitting toward receivers that do not yet exist with the required sensitivity. Each of these challenges is formidable on its own. Taken together, they define an engineering program that would likely require decades of development and funding on the scale of the largest scientific projects ever attempted. On the order of tens of billions of dollars, the $100 million allocated to Breakthrough Starshot was intended for research, not construction. It was a budget to explore feasibility, not to build the system itself. And even if the project had succeeded in every respect, the mission it proposed would still be extremely limited. A probe with a mass of only 1 gram, traveling at 20% of light speed, has no way to slow down. There is no onboard fuel for deceleration. There is no capability to enter orbit around Proxima Centauri or any other body in the system. The probe would pass through at around 37,000 miles per second, and the entire window for close observation would last only a few hours at most. Everything it observes must be captured within that brief moment and transmitted back across 4.24 light-years. Using a communication system powered at only milliwatt levels, the data returned from such a flyby would still be scientifically valuable. Any image captured from within the Alpha Centauri system would be historic. But the mission itself would resemble more a projectile passing through a space and taking a single snapshot, rather than a sustained exploration. There would be no time for extended study, no opportunity for follow-up observations, no close-range investigation, no sample collection, and no ability to adjust the trajectory in response to new discoveries. It would be a single, fleeting encounter with a star system roughly 25 trillion miles away, and even this minimal level of achievement depends on technologies that do not yet exist. Let us move beyond light sails for a moment and focus on what higher speeds truly demand, because energy is the real gatekeeper of interstellar travel. And the burden grows more severe with every increase in velocity. The kinetic energy of a moving object scales with the square of its speed, double the velocity, and the energy requirement increases fourfold, triple it, and the requirement rises 9 times. At interstellar scales, this relationship becomes unforgiving. We saw earlier that accelerating a single kilogram of mass to 1% of the speed of light requires about 4.5 trillion joules, roughly equivalent to the energy of 1 kiloton of TNT. For a spacecraft weighing 1,000 kilograms, that rises to about 4.5 quadrillion joules. Now extend that calculation. At 5% of light speed, the same 1,000 kilogram spacecraft carries around 112 quadrillion joules of kinetic energy, comparable to roughly 27 megatons of TNT, similar to the largest nuclear detonations ever recorded. And this is for a vehicle with a mass not much greater than a compact car. At 10% of light speed, the energy climbs further, reaching roughly 450 quadrillion joules, equivalent to more than 100 megatons, exceeding the yield of the most powerful thermonuclear devices ever tested. For a payload of just 1 metric ton, the energy requirements already reach extreme levels. At 20% of light speed, the target proposed by Breakthrough Starshot, the energy per kilogram rises to around 1.8 quadrillion joules. For a gram scale probe, this remains within the realm of possibility. The total energy delivered during the brief laser acceleration phase is on the order of a few terajoules, comparable to a fraction of a kiloton explosion. Intenser, but not beyond the capabilities of a sufficiently powerful laser system. But the situation changes immediately when the mass increases. Imagine scaling up from a gram-scale chip to a real spacecraft, something carrying instruments weighing tens of kilograms, or a probe, in the hundreds of kilograms, capable of slowing down and entering orbit, or even a crewed vehicle with a mass in the tens of thousands of kilograms, designed to support human life. The energy requirements do not grow gradually. They surge. A 100-kilogram probe traveling at 20% of light speed would require on the order of 1.8 times 10 to the 17th joules, comparable to the annual electricity production of a mid-sized European nation. A 10,000-kilogram spacecraft would require around 1.8 times 10 to the 19th joules. That already exceeds the yearly energy consumption of many countries, and a 100,000-kilogram vehicle at the same speed would demand roughly 1.8 times 10 to the 20th joules, approaching the total annual energy usage of the entire world, concentrated into a single propulsion event. And all of these estimates assume perfect efficiency, every unit of energy converted directly into motion, with no losses. In reality, propulsion systems waste significant amounts of energy as heat, exhaust, radiation, and structural stress. Practical efficiencies might fall to 10 or 20%, meaning the total energy required could be 5 to 10 times higher. The barrier does not ease as speed increases. It becomes even more rigid. Every additional fraction of light speed demands far more energy than the one before. The relationship is not linear. It follows a curve that rises more steeply with each increase in velocity. As speeds approach a meaningful fraction of light speed, relativistic effects begin to matter. The effective mass of the spacecraft increases according to the Lorentz factor, requiring even more energy for each further gain in speed. This is why propulsion is not simply an engineering challenge waiting for a clever breakthrough. It is a problem rooted in the fundamental structure of physics itself. The energy cost of interstellar travel is governed by laws that cannot be bypassed or negotiated. Technologies can improve. Efficiency can increase. Spacecraft can be made lighter, but the underlying equation remains, and it sets a minimum energy threshold that no system can avoid. But energy is only part of the velocity problem. There is another side that is often overlooked, and it may be even more difficult. It is the problem of stopping. All of the energy calculations so far assume a one-way acceleration. The spacecraft reaches its cruising speed and then continues at that velocity until it arrives. This is the approach taken by concepts like Breakthrough Starshot. Accelerate once and never slow down. But a flyby is not a complete mission in any meaningful scientific sense. If you want to enter orbit around a star or a planet, if you want to land, or remain in place for extended observation, then the spacecraft must slow down. And in the strict mathematics of rocketry, deceleration is not a small addition to the energy budget. It at least doubles it. And in realistic scenarios, the penalty is far greater. The reason lies in the Tsiolkovsky rocket equation, the fundamental principle that governs all reaction-based propulsion. This equation shows that the velocity a rocket can achieve depends on the speed of its exhaust and the ratio between its initial mass and its final mass after burning fuel. To reach higher speeds, the amount of fuel required grows exponentially compared to the payload. This is not a simple linear increase, but a compounding one, where each additional gain in velocity demands a disproportionately larger amount of fuel. Now consider what it means to slow down. A spacecraft that accelerates to 10% of light speed and then needs to stop at its destination must carry enough fuel not only to reach that speed, but also to cancel it out completely upon arrival. That fuel for deceleration must itself be carried during the acceleration phase, which means it also has to be accelerated to full speed. That added mass requires even more fuel to move it, which in turn requires still more fuel. The effect compounds rapidly. For a spacecraft relying on onboard propulsion at 10% of light speed, the ratio of fuel to payload can grow into the thousands, or even tens of thousands, depending on the efficiency of the engine. A spacecraft designed to both accelerate and decelerate is not simply a vehicle carrying additional fuel. It becomes a structure composed almost entirely of fuel, with the actual payload reduced to a very small fraction of the total mass at launch. This exponential penalty is the reason Breakthrough Starshot adopted a flyby approach. Attempting to slow a gram-scale probe from 20% of light speed using any known onboard propulsion method would require so much fuel that the entire concept breaks down. The probe would need to carry many times its own mass in propellant, eliminating the very advantage of being lightweight. And even if an appropriate propellant were available, the sail-based acceleration method offers no way to decelerate at the destination. The laser remains on Earth, pushing the sail outward. There is no corresponding system at Alpha Centauri to slow it down from the opposite direction. Some ideas have explored using the light from the destination star itself to slow a sail, or using magnetic fields to interact with the interstellar medium as a form of braking. These proposals are theoretically interesting, but they remain untested and face significant practical challenges. The pressure from starlight is far too weak to meaningfully slow a probe arriving at 20% of light speed. Magnetic braking would require enormous superconducting structures and would only be effective at much lower velocities. This means that all of the energy calculations discussed so far apply only to the simplest possible mission profile. A one-way flyby with no capacity to slow down, enter orbit, or return. Any mission that aims to do more than pass through the Alpha Centauri system at roughly 37,000 miles per second and capture a brief snapshot must carry enough energy not only to arrive, but to stop. And the cost of stopping is not a simple addition. It multiplies the challenge. Under realistic conditions, it can increase the total energy requirement by an order of magnitude or more. This is why the distinction between a flyby and a true exploration mission is so critical. A flyby is what remains when the distance has already imposed its limits, and you accept a brief glimpse instead of a sustained presence. En exploration mission, one that enters orbit, deploys instruments, and studies the system over time, depends entirely on solving the problem of deceleration. And solving that problem at interstellar speeds requires energy budgets that exceed even the already immense requirements for acceleration alone. And then, there is one more dimension that is often set aside: communication delay. The speed of light is not only a limit on travel, it is also a limit on communication. Any signal, whether a radio transmission or a laser pulse, moving between Earth and Alpha Centauri travels at exactly that speed. No faster, no exceptions. The one-way delay is 4.24 years. A full exchange, a question sent and a response received, takes about 8.5 years. This means that any probe operating at Alpha Centauri is effectively isolated during its encounter. Controllers on Earth cannot guide it in real time. They cannot adjust its instruments based on what it observes, nor can they redirect its path in response to unexpected conditions. Every decision must either be programmed in advance or handled autonomously by onboard systems. In that moment, the probe is entirely on its own. For a simple flyby mission, this limitation can be managed. The task is straightforward: point the instruments forward and transmit whatever data can be captured. But for more complex missions, the communication delay becomes a serious constraint. Imagine a future probe attempting to enter orbit around Proxima Centauri b, an Earth-sized world within the star's habitable zone. Orbital insertion requires precise timing, careful velocity adjustments, and responses to conditions that cannot be fully predicted from Earth. If the probe encounters an unexpected debris field, a dust structure, or a magnetic environment that disrupts its systems, it must identify and respond to the situation on its own. Any request for guidance sent back to Earth will not be answered for more than 8 years. Now extend this to a human mission. Imagine a crew arriving after decades of travel. They begin their work, start observing the system, and then encounter something unanticipated: a medical crisis, a system failure, a navigational threat. They send a message to Earth, describing the situation and asking for assistance. That message reaches Earth 4 years, and a few months later, engineers analyze the situation, develop a response, and send instructions back. Those instructions arrive at Alpha Centauri another 4 years, and a few months after that. More than 8 years have passed since the original problem occurred. Whatever the situation was, it has already been resolved, one way or another. The crew survived or did not, succeeded or failed, relying entirely on their own resources. This is a level of operational isolation that no human mission has ever experienced. For comparison, the Apollo missions to the Moon involved a communication delay of just over 1 second. Noticeable, but easily managed. A crew on Mars would experience communication delays ranging from 4 to 24 minutes, depending on orbital alignment. Difficult, but manageable with autonomy and careful planning. A crew at Alpha Centauri would face delays of more than 4 years. That is no longer a communication challenge. It is a complete separation. The crew is effectively cut off from Earth. They cannot call for assistance, they cannot receive supplies, and they cannot be rescued. They become the most isolated human beings ever to exist, separated from home not only by distance, but by time itself. The psychological consequences are rarely explored, but they may be profound. Humans evolved as social beings, deeply connected to communities. Even astronauts aboard the International Space Station, only a few hundred miles above Earth, report isolation and psychological strain during missions lasting just 6 months. Submarine crews on extended patrols experience measurable mental stress. Researchers stationed in Antarctica during the long winter months show increased rates of depression and cognitive decline. Now imagine a crew that knows, with complete certainty, that no help can arrive for decades, that no message from loved ones will reach them in less than 4 years, that every decision, every emergency, every moment depends entirely on the people and resources within the spacecraft. This is not exploration in any familiar historical sense. When early explorers crossed oceans, they could stop, resupply, and interact with other societies. When polar expeditions reached the Antarctic interior, They knew rescue might take months, not decades. A crew traveling between stars has no such options. There are no ports, no supply chains, no rescue missions waiting beyond the horizon. No one is coming. The distances are simply too vast, and this isolation is not limited to human crews. Even robotic probes at Alpha Centauri would operate in a level of independence unlike anything in previous space missions. Every rover on Mars eventually receives updated instructions, software patches, and troubleshooting support from Earth. The delay is measured in minutes, not years. At Alpha Centauri, a robotic probe would need to be equipped with enough intelligence and enough built-in contingency planning to handle every possible situation on its own. It would effectively become an independent scientific agent, capable of deciding what to observe, how to react to unexpected conditions, and how to allocate its limited resources. The level of artificial intelligence required for that kind of autonomy does not yet exist. We are still decades away from systems that can match the judgment of experienced mission controllers. And even if such systems are developed, there is no way to fully test them against the real conditions at Alpha Centauri before the probe arrives. There is another layer to the communication problem that goes beyond delay. It is bandwidth. The amount of data a probe can send back depends on its transmitter power, the size of its antenna, the sensitivity of receivers on Earth, and the distance the signal must cross. At interstellar distances, the achievable data rates become extremely low. A nanocraft similar to those proposed in Breakthrough Starshot, transmitting with only milliwatts of power across 4.24 light-years, might achieve data rates of only a few bits per second, even under optimistic assumptions. At that speed, transmitting a single high-resolution image could take weeks, or even months. Even a larger probe, equipped with a more powerful transmitter and a larger antenna, would still face strict limitations on bandwidth. With current and near-term technology, data transmission across interstellar distances would be measured in bits per second, not megabits. A mission that collects vast amounts of scientific data over time might require decades just to send that information back to Earth. The scientific return is limited not only by what the probe can observe, but by how much of that data can realistically be transmitted across the void. This is the layered reality of interstellar distance. It is not a single obstacle, but a chain of interconnected challenges, each one reinforcing the next. The distance demands extreme speed. Extreme speed demands enormous energy. Enormous energy forces a choice between very small payloads or infrastructure on the scale of entire civilizations. Small payloads limit what can be learned. Larger payloads push energy requirements beyond what we can achieve. Any speed below light speed introduces years of communication delay. And that delay removes the possibility of real-time control, forcing every mission to rely on full autonomy. Autonomous operation requires a level of artificial intelligence that we have not yet developed. And even when such a probe gathers data, that information can only return to Earth at speeds that would seem painfully slow. Even by the standards of early internet connections, every one of these limitations exists at Alpha Centauri, the nearest star, not at some distant system dozens or hundreds of light-years away, but at the most accessible target in the entire interstellar catalogue, just 4.24 light-years from us. About 25 trillion miles, and none of these problems have been solved. Not one. At this point, there is a natural temptation to lean into optimism, to argue that technology progresses exponentially, that what feels impossible today may become routine in the future, that the pioneers of early flight could not have imagined modern aircraft, and therefore we should not assume our current limits are permanent. There is some truth in that perspective. Technology does advance, and challenges that once seemed insurmountable can yield to innovation over time. But the problem of interstellar distance is fundamentally different from the problem of early aviation. The Wright brothers needed only to generate enough lift to overcome gravity at relatively low speeds. The physics was already understood. The gap between theory and practice was narrow. Interstellar travel, by contrast, requires generating enough energy to cross a gulf so immense that even light takes years to traverse it. The gap is not narrow. It spans entire orders of magnitude. Even the most optimistic propulsion concepts demand energy levels that exceed the total output of modern civilization. The physics is not waiting for a clever workaround. The physics itself is the obstacle, and Alpha Centauri remains unchanged. It does not respond to our expectations or our timelines. It sits in the southern sky, bright and steady, exactly 4.24 light-years away, neither moving closer nor farther in any way that matters on human timescales. It will still be there if we solve these challenges, and it will still be there if we do not. The distance remains what it is, a vast stretch of empty space, waiting for a species that has yet to cross even a tiny fraction of it. So the question is not whether we will one day reach Alpha Centauri. That belongs to the future. What matters now is what its distance reveals about the universe we inhabit, and about the true nature of interstellar space. That understanding begins with a simple realization. This is the nearest star system, and it already demands more than we can currently achieve. Everything else lies even farther beyond. In August of 2025, a team of astronomers using NASA's James Webb Space Telescope reported findings that may prove to be among the most significant in the study of exoplanets. Using the telescope's mid-infrared instrument, astronomers identified a faint point of light near Alpha Centauri A that appears consistent with a gas giant planet. Roughly comparable in mass to Saturn, it seems to orbit its star at about twice the distance between Earth and the Sun, placing it within what would be considered the habitable zone of Alpha Centauri A. If the detection is confirmed, if verified, this object would become the nearest, coldest, oldest, and lowest mass exoplanet ever directly imaged beyond our solar system. The research describing the observation has been accepted for publication in the astrophysical journal Letters. The response from the scientific community has been a mix of excitement and caution, because confirmation has not yet been achieved. The sequence of observations is revealing. The initial detection took place in August of 2024. Follow-up observations were then conducted in February and April of 2025. In both cases, the candidate object was not seen again. It appeared to have disappeared. However, simulations exploring millions of possible orbital paths showed that in about half of all stable configurations, the planet would have been positioned too close to Alpha Centauri A during those follow-up, lost within the star's glare and therefore undetectable. Its absence did not contradict the hypothesis. Instead, it was consistent with a body moving along an elliptical orbit, temporarily hidden from view. The team also incorporated an earlier observation from 2019, made using the European Southern Observatory's Very Large Telescope, which recorded a similar point of light in a nearby position. If both detections correspond to the same object at different points along its orbit, then the combined data suggest a planet with a mass similar to Saturn, an orbital period somewhere between 1.5 and 2.5 years, and a moderately elliptical orbit. This object remains a candidate. It could still prove to be an instrumental artifact, a concentration of dust, or a statistical anomaly. The researchers themselves describe it carefully as a possibility, not a confirmed discovery. The next opportunity to test the observation comes in August of 2026, when the object, if real, should once again appear in a detectable position for the James Webb Space Telescope. If it does, the confirmation would be historic. If it does not, it may simply become another intriguing signal that ultimately fades into uncertainty. But even the possibility reshapes how we think about the distance. Alpha Centauri is no longer just an abstract nearest star system. It may host a gas giant within the habitable zone of a sun-like star, and where such planets exist, moons may also exist. Moons with atmospheres, moons with liquid water, moons with the chemical conditions that, on at least one known world, gave rise to life. This is not a distant system hundreds of light years away. This is the neighboring star, visible to the naked eye under clear southern skies, whose light reaches us in just over 4 years. and the James Webb Space Telescope suggests that it may contain a planetary system more complex than we once imagined. Proxima Centauri, the closest individual star, is already known to host at least 2 confirmed planets. Proxima Centauri b, identified in 2016, is a planet roughly similar in size to Earth and orbits within the region around its star where liquid water could, in theory, exist on a rocky surface. Proxima Centauri d, a much smaller world with a mass close to a quarter of Earth's, was first detected in 2022 and later confirmed in 2025. A third candidate, Proxima Centauri c, possibly a super-Earth or a small Neptune-like planet on a much wider orbit, has been proposed, but remains unconfirmed as of 2025, with observations unable to verify its presence. Even the most promising of these worlds, Proxima Centauri b, carries a level of uncertainty that cannot be resolved from a distance of 4.24 light-years. It does lie within the habitable zone, but that term refers only to temperature, the range where liquid water might exist under the right atmospheric conditions. It does not guarantee the presence of water, an atmosphere, or any of the ingredients necessary for life. And in the case of Proxima b, there are strong reasons for skepticism. Proxima Centauri is not a stable star like our Sun. It is a red dwarf flare star, highly active and prone to violent outbursts. It produces powerful flares regularly, sudden bursts that can increase its brightness dramatically within minutes and flood nearby space with intense ultraviolet and X-ray radiation. In 2018, astronomers recorded a superflare from Proxima Centauri that released around 10 times more energy than the strongest solar flares ever observed from the Sun. These events are not rare. They occur multiple times each year, sometimes even more frequently. Any planet close enough to Proxima Centauri to receive enough heat for liquid water is also close enough to be repeatedly exposed to these eruptions. The consequences for habitability are severe. Ultraviolet radiation can break down complex molecules on the surface, while repeated X-ray exposure can gradually strip away a planet's atmosphere over long timescale. Simulations of Proxima b's atmospheric evolution suggest that it may have lost its atmosphere entirely within the first few 100 million years of its history, leaving behind a barren, exposed surface with no protection from radiation. Some models allow for the possibility that an atmosphere could survive, but only under specific conditions, such as a strong magnetic field or an unusually dense original atmosphere. These scenarios remain uncertain. We do not know whether Proxima b possesses a magnetic field. We do not know what its atmosphere was like in the past. We do not know whether any atmosphere exists today. There is also the issue of tidal locking, because the planet orbits so close to its star, completing a full orbit in about 11 days. It is almost certainly locked in such a way that the same side always faces the star. This results in one hemisphere in constant daylight, while the other remains in permanent darkness. The temperature difference between these regions could be extreme, with intense heat on one side and deep cold on the other. Whether atmospheric circulation could redistribute heat enough to create habitable conditions in some regions remains an open question, with different models producing different outcomes depending on their assumptions. The most honest scientific assessment of Proxima Centauri b, as of now, is this. It is an Earth-sized world located within the habitable zone of the nearest star, and it could be nothing more than a barren surface, stripped of its atmosphere, scorched by radiation on one side and frozen solid on the other. It could also be a planet with a dense atmosphere, active weather patterns, and liquid water across parts of its surface. We simply do not know. The data we can gather from Earth, even using the most advanced telescopes available, cannot clearly distinguish between these possibilities. Answering that question almost certainly requires direct observation from within the system, a probe close enough to study the planet's atmosphere, surface, and magnetic environment in detail. This is perhaps the most frustrating aspect of the distance problem. The nearest potentially habitable planet may or may not support life, and the only definitive way to find out is to cross roughly 25 trillion miles of empty space and examine it directly. The question can be answered in principle. The distance prevents us from answering it from here. So the nearest star system to our Sun contains at least 2 confirmed planets around Proxima Centauri, along with a strong candidate orbiting Alpha Centauri A. There may be additional worlds yet to be discovered. Radial velocity measurements have placed increasingly strict limits on unseen planets in the system, ruling out larger bodies across many orbital paths. But current detection limits still allow for smaller, rocky planets that remain beyond our ability to observe. The Alpha Centauri system may host an entire collection of worlds, some rocky, some gaseous, some potentially habitable, all orbiting within a stellar system that is, in cosmic terms, right next door. We can observe these planets, estimate their masses, and constrain their orbit. Within the coming years, we may begin to analyze their atmospheres using spectroscopy, searching for chemical signatures such as oxygen, methane, carbon dioxide, or water vapor that could hint at biological processes. The James Webb Space Telescope and future observatories, including the Nancy Grace Roman Space Telescope expected to launch in 2027, are designed for exactly this kind of investigation. The era of studying exoplanet atmospheres in the Alpha Centauri system is not distant. It is already beginning. And this is where the distance becomes more than just an obstacle. It becomes a source of something deeper, almost a form of frustration built into the structure of reality. We can see these worlds. We can study them from afar. We can determine their sizes, their orbits, their temperatures, and perhaps even the composition of their atmospheres. But we cannot go there. We cannot send a probe that arrives within a human lifetime using any technology we currently possess. We cannot place instruments on their surfaces. We cannot collect samples from their soil or atmosphere. We cannot confirm, with certainty, whether any of these worlds host life, because definitive evidence of biology likely requires direct, close-range analysis. The universe has placed potentially habitable worlds at the nearest possible stellar address, and then separated that address from us by an immense expanse of empty space. The invitation is visible. The path is not. This tension between what we can observe and what we can reach is not unique to Alpha Centauri, but it is felt most strongly there, because the stakes are so high. Alpha Centauri is the test case. If we cannot reach the nearest star system, then reaching any star system remains beyond us. Every other destination in the interstellar catalogue lies farther away, most of them by a significant margin. Barnard's star, the next closest single star system, is about 6 light-years distant, nearly 50% farther than Proxima Centauri. Wolf 359 sits at roughly 7.9 light-years, and Lalande 21185 lies beyond 8 light-years. Sirius, the brightest star in our sky and a system studied for thousands of years, is about 8.6 light-years away, more than twice the distance to Alpha Centauri, and these are still considered our immediate neighbors. The nearest star known to host an Earth-like planet in its habitable zone, beyond Proxima Centauri b, may lie tens or even hundreds of light-years away. The Milky Way itself spans about 100,000 light-years. Most of its hundreds of billions of stars are separated from us by distances that make 4.24 light-years seem almost negligible. If reaching the nearest star already demands 74,000 years at current speeds, or requires energy on the scale of entire civilizations at higher speeds, then the wider galaxy is not a frontier in any practical sense. It becomes something closer to a confinement. The barriers are distance itself, measured in light-years. This is the deeper realization forced by Alpha Centauri. It is not just that one nearby star is far away. It is that the spacing between stars, the fundamental structure of the galaxy, is set on a scale that far exceeds the capabilities of any technology humanity has ever created or is currently developing. The galaxy is not a dense network of reachable destinations. It is an immense expanse of emptiness, with small islands of stars scattered across it, separated by distances that even light requires years to cross. The numbers make this clear. The average separation between neighboring stars in our region of the Milky Way is around 4 to 5 light-years. Alpha Centauri is not unusually distant. It is typical. The nearest star happens to be about as far away as stars generally are from one another in this part of the galaxy. There is no hidden closer system waiting to be discovered just beyond our current observations. There is no unseen neighbor at half a light-year that has somehow escaped detection. The density of stars near the Sun is what it is, and it places even our closest neighbors at distances far beyond anything in human experience. Closer to the center of the galaxy, stars are packed more tightly together. In those regions, separations can shrink to fractions of a light-year. Within globular clusters, the average distance between stars can fall to around 1/10 of a light-year, but even these reduced distances still represent trillions of miles. And those environments bring their own difficulties: intense radiation, instable gravitationnelle conditions, and stellar surroundings that may be hostile to life. Denser regions are not necessarily easier for interstellar travel. They are simply places where the emptiness between stars is slightly less overwhelming. Let us now face the most uncomfortable implication. Alpha Centauri is the easiest interstellar destination humanity will ever encounter. This is not pessimism. It is geometry. The nearest star system is, by definition, the one that demands the least energy, the shortest travel time, and the smallest communication delay. Every other system requires more of all three. If even the nearest target already lies beyond our current capabilities, then the difficulty curve of interstellar travel does not begin at manageable and rise to difficult. It begins at overwhelming and rises into the unimaginable. Consider a mission to a star just 10 light-years away. At Voyager-level speeds, the journey would take more than 175,000 years. At 1% of light speed, it would still take around 1,000 years. At 10% of light speed, the trip would last about 1 century. The energy required increases directly with distance at a fixed velocity, meaning a mission to 10 light-years would demand more than twice the energy needed for Alpha Centauri at the same speed. Communication delays would also double, stretching to over 20 years for a full exchange. Every challenge we have already examined, energy demand, travel duration, communication delay, material degradation, and navigation precision, becomes proportionally more severe. And 10 light-years is still considered nearby. Now consider stars more similar to our Sun, systems that might host planets like our own. These may lie 20 or 30 light-years away. At 10% of light speed, reaching such a system would take 2 to 3 centuries. Communication delays would stretch across 40 to 60 years. The energy requirements would multiply several times beyond those already required for Alpha Centauri. At that point, we are already dealing with multi-generational timescales and energy commitments on the scale of entire nations, and we have barely moved beyond our local region of space. Push farther still, the nearest major spiral arm of the galaxy lies thousands of light-years away. The center of the Milky Way is about 26,000 light-years distant. The far side of the galaxy extends tens of thousands of light-years beyond that. At 10% of light speed, a journey to the galactic center would take around 260,000 years. Crossing the full width of the galaxy would require roughly 1 million years. These are not travel times in any meaningful human sense. They are evolutionary timescales. Entire species rise, transform, and disappear in less time than such a journey would take. The galaxy is not something we traverse. It is something we inhabit locally, like a living organism confined to a single region within a vast body. We can observe the larger structure, we can map it, measure it, and study its behavior. But we exist within one small neighborhood, and the distances to all others are so immense that they impose something like a natural barrier, a kind of cosmic isolation. Not a quarantine imposed by any authority, but one enforced by the geometry of space itself. This is the lesson Alpha Centauri offers, and it is not easily softened by optimism about future technology. The universe is structured in a way that makes observation relatively simple, but physical access extraordinarily difficult. We can observe stars across the galaxy with modest instruments. We can detect planets orbiting stars hundreds of light years away. We can analyze the atmospheres of distant worlds through spectroscopy. We can even listen for potential signals from civilizations across vast distances. Seeing, in this sense, is easy. The universe is generous with light. But reaching is something else entirely. Photons have no mass. They move at the speed of light naturally. They require no effort to send and none to receive. Spacecraft are fundamentally different. They have mass. They must be accelerated with enormous energy. They contain systems that wear down, structures that age. And if they carry humans, they must support life with food, water, air, and psychological stability. The cost of moving matter across interstellar distances is not remotely comparable to the cost of receiving light from those same distances. The imbalance is profound. We can capture images of planets around Alpha Centauri using telescopes that cost billions of dollars and operate far from Earth. But we cannot physically reach those planets with any level of resources currently imaginable. There is a deeper implication here, one that is best approached carefully. The universe appears, whether by design or by natural evolution, to favor visibility over accessibility. Stars emit light continuously across immense spans of time. Planets reveal themselves through transits, gravitational effects, and thermal signatures. Galaxies can be observed across billions of light years, and the cosmic microwave background preserves a snapshot of the early universe. Information moves freely across space at the speed of light. Matter does not. Matter remains bound within local gravitational systems unless vast amounts of energy are used to move it. The energy required to transport matter between stars is so extreme that it effectively divides the galaxy into isolated regions, each centered on a star system, each separated by distances that allow light to pass freely, but resist the movement of anything with mass. If you were to design a universe that frustrates interstellar travel while rewarding observation, it would be difficult to improve on the one we inhabit. The sky is filled with destinations. The space between them is almost entirely empty. You are free to look in any direction, but you are able to travel to almost none of them. Alpha Centauri expresses this reality more clearly than any other object we can see, precisely because it is the closest star. It represents the lower bound of distance itself. It is the most favorable case, the simplest version of the interstellar challenge, the one that every other destination only makes more difficult, and even this case, by every engineering measure we possess, remains out of reach. This does not mean that interstellar travel is forever impossible. Physics does not prohibit it. The speed of light allows a crossing of 4.24 light-years in just over 4 years. And relativistic effects can shorten the experience duration for travelers moving at extreme speeds. There is no fundamental law that prevents a spacecraft from reaching Alpha Centauri. What exists instead is a practical reality. Achieving such a journey requires levels of energy, engineering capability, and long-term commitment that no human civilization has yet demonstrated. Perhaps a future civilization will. Advances in fusion energy, antimatter, energy storage, laser propulsion, or entirely new areas of physics could change what is possible. It would be unwise to claim that the problem can never be solved, because history contains many examples of challenges once thought impossible that were eventually overcome. But it would be equally unwise to assume that the problem will solve itself simply because we want it to. The distances between stars are not engineering problems in the same sense as building infrastructure or launching satellites. They arise from the fundamental geometry of the universe itself. Shaped by the distribution of matter in the galaxy, the processes of star formation, and the limits imposed by relativity, these are not variables that technology can adjust. They are conditions that all technology must operate within. Alpha Centauri is 4.24 light-years away. That distance was not arranged to suit human exploration. It is simply the result of how stars formed billions of years ago in this region of the galaxy. The distance carries no intention. It carries no intention. It does not care about human ambition, or curiosity, or desire. And that quiet indifference may be the most important lesson hidden inside the distance. The universe does not scale itself to meet the abilities of those who arise within it. It does not space its stars in ways that are convenient for civilizations that happen to emerge on small, fragile worlds. The distances between stars are not arranged, they simply are, a consequence of physics, not a feature designed for us. Whether we experience that as wonder or as unease says more about us than it does about the cosmos. But one thing remains undeniable. The distance to Alpha Centauri is not just large, it is revealing. It tells us something fundamental about the nature of reality. A universe where light moves freely, effortlessly crossing the void, while matter remains bound, heavy, and costly to move. A universe where information flows at the speed of light, but machines advance slowly by comparison, inching forward against enormous resistance. Where the nearest star shines clearly in the night sky, visible without any instrument, yet remains unreachable by every technology we have ever created. And the unsettling part is not the number itself. 25 trillion miles is just a figure. It can be written, spoken, converted, simplified. Numbers are easy. What gives that number weight is what it represents. This is not the distance to some distant, forgotten corner of the galaxy. This is the closest possible destination, the nearest, the baseline, the simplest case nature offers us. And it is already beyond us. Everything else is farther. Every other star demands more. More time. More energy. More isolation. More uncertainty. More commitment than this one. There are no exceptions. So if the easiest path is already this steep, then everything beyond it disappears into something far more difficult to imagine. That is what Alpha Centauri ultimately shows us. Not just a distance, but a boundary, a glimpse into how the galaxy is built. The stars are close enough for us to study, and far enough to remind us where we stand, and the closest of them all, glowing softly in Centaurus like a distant beacon, is already so far away that reaching it would stand as the greatest physical accomplishment any civilization could ever achieve. 4.24 light-years, about 25 trillion miles, hundreds of thousands of times the distance between Earth and the Sun, 74,000 years at the speed of Voyager, more than 4 centuries at 1% of light speed, just over 2 decades at 20% of light speed. Using technologies we have not yet built, sending something no heavier than a few grams, rushing past its destination in a matter of hours, with the first whisper of data taking years to return. This is the nearest star. This is the simplest case. This is where interstellar space begins. And even here, at the very edge of what should be possible, the scale of the universe stretches beyond anything the human mind was ever built to truly hold.